and wrap up Unit 4. We're going to start off with alternating series. Let's go. The integral test and limit comparison test do not apply to series that have negative terms. For example, they can't be used in a common series such as this one below. An alternating series is one whose terms alternate from positive and negative values, such as written here and here. Take note of this term over here. When n is 1, this negative 1 will be to the power of 2, thus making the first term positive. When n is 2, this will be 2 plus 1, 3, which will make this negative 1 come out as negative 1, which makes the second term negative, and so on. Here we see a similar pattern going on, but instead it's to the power of n. So, the gimmick with these, right? I wonder if you all heard that. I just dropped something under the under my desk. But it's fine for now. Okay. And also, sorry. Okay. So what these guys over here is called the alternating term. The alternating term can take forms like this, and we just know that it's something where it just flip-flops, where it goes from positive to negative, almost like in patterns. So there's one not simple alternating term that I've snuck in your group work, but just know that for every index, it switches from negative to positive. So, for example, -1 to the power of n, -1 to the power of n plus 1. If I were to do something like sine of pi n, where we know the pi lets it flip between 0 to 1 to not 0. Actually let's make it, yeah, I don't know why I was doing half a pi. So 0 and then let me change it. There you go, 1/2. So we go 1/2 to 1, and another 1/2 to -1, and 1/2 to 1, and 1/2 to -1, etc. So stuff like these. Oh, and then where each bn is positive, and we call that the non-alternating part. So that's the alternating term, or I guess part. This is the non-alternating part. So we're called the harmonic series. Now, an adjustment we can make to the harmonic series is called an alternating harmonic series. The alternating harmonic series is called the alternating harmonic series. That's just the title, that's just the name. I'm sorry. Unlike the harmonic series, this one converges. Why? Well, let's just pay attention to its sum and make this number line starting from 0, 1/2, and 1. Now, when I do S1, so I'm just adding the first term, it's going to be over here, S1. And then I'm going to go ahead and add the second term. What is S2? Well, that's 1 minus 1/2, so that's just going to be S2. And then I'm adding 1/3. So if I'm adding 1/3 to 1/2, that's going to be over here. Let me get the actual number for that real quick. So S1 is 1, S2 is 1 minus 1/2, which is 1/2. S3 is, I'm going to write as this S2 plus the third term, which is 1/3. So 1/2 plus 1/3. That's going to be 5/6. So maybe we just say 5/6 is over here. S3. And we'll say this is 5/6. And then if I'm doing S4, that's S3 plus the fourth term, which is minus 1/4. So 5/6 minus 1/4. That's going to be 19 over, was that 24? Let me just double check. Yes. Okay. And 19 over 24, it's not above I mean, it's above 1/2, but it's not, beyond 1. So that means it's probably going to be in between 1. I'm pretty sure it's in between 5, 6 because we subtracted from 5, 6. So it's going to go here. And this would be S4. Now I'm going to stop at S4 and just pay attention to that idea that we're adding and subtracting a smaller and smaller and smaller term. To where eventually, and I'm going to do this with the second color because so you know I didn't actually plot it, we're going to have this sort of looping pattern. And if we keep looping with the idea that we're getting smaller and smaller loops, then technically we should start to converge almost in this spiral effect. So, the explanation of why the alternating harmonic series converges relies on two properties of the 1 over n series. First, the values of 1 over n are decreasing. For every time we go up the n, we are getting a smaller and smaller fraction. And also, the limit of 1 over n goes to 0. So we know that eventually we're just going to keep adding smaller and smaller terms. And they're sequential, meaning that, after adding the second term, we're getting a smaller term that's below the second, but not that's not smaller than the fourth, and etc. We are just steadily decreasing. So this brings us to the alternating series test. Suppose you have a series, a sum of a series in this format, or a sum of a series in this format, where this is an alternating series. If the limit of n going to infinity of the non-alternating part goes to 0, and the setup of these series for all n are steadily decreasing, then the series converges. Now, a couple of notations. In some of these realms of mathematics, we let the first couple of terms slide. So, as long, I'm going to add a caveat, as long as n starts eventually decreasing, we can use the alternating series test. Note, if the limit does not equal 0, the test does not apply. However, the series diverges by the divergence test. Because if we are basically saying, well, this is our introduction. We're saying that it's actually an alternating series. And we're saying that Bn does not converge. Then that leads me to believe that with the addition of the alternating term, it definitely won't converge. So we can make this jump of logic. If the values of Bn are not decreasing, the test does not apply. Again, if they are doing everything but decreasing, or if maybe they're decreasing for a little bit, but then they start increasing again, as long as they start decreasing eventually, then you can use the alternating series test. So we're going to do a set of 3 questions. Example 1, determine whether each series converges or diverges using the alternating series test when appropriate. Okay, so here we have the sum of -1 to the power of n plus 1 over n squared. So that tells me that the non-alternating part is 1 over n squared. So this is going to be the part that we're paying attention to. And we want to know the limit of this as this n goes towards infinity. And it's easy to see that with this expression, that the limit as n goes towards infinity, it's bottom heavy, so this answer is going to be 0. Now going back to what does this say? This says that the limit has to equal 0, and it does. So we've technically, by this sort of check, already showed that first part. But now we need to show the second part. Does this steadily decrease? Well, that's a bit trivial, and it's almost in the same cadence as the harmonic series. So you need to show some sort of evidence that they decrease. There's several ways to do it. In some cases, you will be asked, find f prime of x, where this is b, or let me put of n, where this is bn prime, because at the end of the day, you're just using that notation for that function. So you can say, well, that's bn, so 1 over n squared prime. I'm going to rewrite that to be n to the power of negative 2 prime, which is just negative 2, n to the power of negative 3, which we can just go ahead and make negative 2, 1 over n to the power of 3. And for here, because all of our n's are 1 or greater, so because n's are 1 or greater, then negative 2, 1 over n to the power of 3 will for sure be positive. Will for sure be negative. Why? Wait, I was getting my white out. Why? Well, because n to the power of 3, because n is positive, will lead me to believe that n to the power of 3 will always be positive. So a positive, and a negative term interacting via multiplication or division means that that combination, that full product after simplification, will for sure be negative. Another thing you could have done is you could have just used a comparison. You could have just said, okay, well, we know, or we're trying to show that 1 over n plus 1 is less than 1 over n. Because technically you're showing that bn plus 1 is less than bn. Well, you set up here, and then you can go ahead and play with the inequality. For here, you'd probably just do cross multiply. So you get n is less than n plus 1, which here, that's just true. Because we know, n is equal to n. If you add one thing to one side without adding it to the other, you just make that term greater. So you can show it this way, or you can show it this way. It depends on your logic. In some cases, it's not appropriate. In some cases, it is. It really just varies. Okay. Next, 2. So 2 says negative 1 to the power of n times cosine squared of 1 over n. Okay, well, this is the non-alternating part, so I'm going to take the limit as n goes to infinity of cosine squared of 1 over n. With this, I'm going to use the cheat of letting it go inside the function, since really this is going to be the term that's changing. So cosine squared of the limit as n goes to infinity of the term 1 over n. Well, that's going to be 0. So cosine squared of 0 is equal to 1. Now, this, obviously, let me write this just out loud. The limit as n goes to infinity of cosine squared of 1 over n is equal to 1. It does not equal 0. So we have that special technicality that was just discussed, where if it doesn't equal 0, this test does not apply. Yet, the series diverges because of the divergence test. So here you can just, oh, I forgot to explain the convergence part of this. Thus, this sum converges. And then via the alternating series test. And then this sum doesn't converge via the divergence test. Oh, so I didn't. Okay, so I didn't leave your tricky alternating term out of, and I thought I put in the group sheet, or maybe I put in both. I might just put in both and assume one or the other. Can't find it here. Well, either way. Okay, so this is the sneaky alternating part. We know because if I do n to be 1, that's going to be pi. So that'll start off with -1. And then, or here, actually, instead of just saying it, let me write it. Cosine of pi, well, we know that's just -1. Cosine of 2 pi, we know that's going to be 1. Cosine of 3 pi, it's going to be -1. So you keep seeing how that cycle would go. So you could technically rewrite this as -1 to the power of n. Yeah, because it starts at -1. And then times 1 over n squared plus 1. So from here, you're going to see if the limit is equal to 0. We have the limit as n goes to infinity of the non-alternating part 1 over n squared plus 1. This is just the logic of it being bottom heavy, so we know it equals 0. So this leads me to believe that we can check if we can use this along with if it's steadily decreasing for the alternating series test. Okay, so for the alternating series test, what we do is yeah, I'm gonna do both again just for funsies. You can do the derivative of that series, which is just 1 over n squared plus 1, which I'm gonna go ahead and rewrite that as a chain rule setup. So we have, let's see, that's gonna be -1, or just negative, of n squared plus 1 power -2, and then times root of 1 inside that, so 2n. So that could be rewritten as -2n over n squared plus 1, all of which is squared. Now from here, that is going to be negative because of the fact n is always going to be greater than or equal to 1 because we're starting off at that part of the series. And that bottom term, it's squared, so it will always be negative. This will, I mean, positive. This will always be positive, and that guy is our only negative term. So we have one negative term and two positive terms that are adding, or I mean, that are combining via multiplication slash division. So therefore, this guy will always be negative. Or you could just use the logic of checking if the one step in this series, so 1 over, what is that, n plus 1 squared plus 1, is less than 1 over n squared plus 1. This one is for sure uglier, but you could do it. You can just literally go, okay, well, n squared plus, or not, actually, no. I was thinking you have to expand that polynomial, but you kind of actually don't. You could do n squared plus 1, n plus 1 squared plus 1. You can subtract the ones, you got n squared is less than n plus 1 squared. And then you could technically square root both sides. You know that there's no trickery, they're always positive. So you have n is less than n plus 1, which is another kind of just dummy inequality that lets you go from here and claim that they do steadily decrease. The only time where maybe this will be better than this is when this setup is not as obvious or it has like a fault. So I'll let you decide whichever one you want. Um, because I know in the homework they have some trick ones where like it has a little hiccup like when n is equal to 1, n is equal to 2, and then maybe when n is equal to 3, it will start steadily decreasing. And then we write that this sum converges via the alternating series test. Okay. All right. Give me a quick second. I need to step out, so I will be right back. You'll see me in the next part.